All right, physical science, we're back in Mr. B's workshop. This is where I do a bunch of construction of all kinds of wood projects, which is, I just love it. I just love it. It's also a good place to film this series. It's going to help you out, I think, on the chemistry test. So pay attention, focus up, dedicate. Yes, we're not in school, but we are in school. So don't be surprised when we get back together and say it's time for your chemistry test, because the work that you're doing now by checking out these videos will pay off. Pay attention to Canvas, do it in all of your classes, improve your future, prove that you're ready for college by just dedicating to school, even though we're not in a building for school. So let's go ahead and get started. We're on video 2 of the series, Physical Science Series 2. This one is going to be on basics on compounds. You have to know about compounds, you have to know basics. Before we get started, I need all of you to find a periodic table. I don't know, find it on the internet, maybe the one I sent you on Canvas. Just get it and have it minimized, or else get a book that has it. They're all over the place, because we're going to reference it, you're going to need it. So if you don't have a periodic table right now, ready, then hit the pause button. Go get one, minimize it, because we're going to reference it in this video. This won't make sense without it. So go ahead and do that. Go ahead and hit it. Hit the pause button. Are you good? All right, good. Now we're back, and you're ready, and you have your periodic table ready. Let's get the basics on compounds, because so far you guys should know your elements. 45 of them, you should know them by heart. All of them, they're easy. Get them, flashcard them, index card them, get them to where you know all your elements, because that's going to be key, the first step in understanding this. But now we're going to combine elements, and we're going to start with atoms versus molecules. Now, if you're an atom, you're one. All right, you're one atom. We're going to talk about like specific elements. Like carbon has an atom, the carbon atom. Oxygen is an atom. One of them is an atom. But if you combine two or more, you make what we call a molecule, which is a compound of atoms. All right, so in other words, if I am like, say, hydrogen, and I'm just one hydrogen, number one, then I'm an element. But if I combine with something else, if I combine with like hydrogen peroxide, I'm now no longer just an element. Now I'm a compound. I've made a molecule. Okay, I've made a molecule. So you got to know the atoms are just one of the elements, so it's one element. And then, but if you combine the elements with anything else, you make a compound or you make a molecule. Either word works fine for me. You make a compound or a molecule. All right, so that's the basic you have to get. In other words, let's see this on the board. You have this atom that's oxygen, and you know this. O is oxygen. It's so easy. All right, and this is assuming there's only one, because if you don't write a number here, if you don't write anything there, then you know that just by writing it, there's at least one. So we're talking about one oxygen atom. This is an element, an atom, oxygen. But you could have a molecule like O2. This is two or more elements combined together to make a molecule. This is a compound. You've combined things, you make a molecule or a compound. So this is a compound, but this is an element. You could also have this, carbon. If I write it like this, carbon, you know there's one, because I didn't write one because I wrote C. You know there's at least one. And you could also have this element, or atom, oxygen. You know there's only one. But you could combine these to form a molecule. And the molecule that many of you are already on, you already know it, versus is CO2. And many of you can tell me this is called carbon dioxide. Carbon dioxide, we breathe it out. So this is a molecule, but these are individual elements. Individual elements or atoms of carbon and oxygen form a molecule called carbon dioxide. So that's a basic, and you have to get that basic for us to get further on in this. All right. So we're going to our next topic, and our next topic is going to be stability. Stability. If you were going to ask a bunch of atoms, say carbon, say oxygen, say lithium, say chlorine, say whatever, if you're going to ask them what they want, and there's this whole classroom of atoms just sitting there, and you said, what do you guys want? They would raise their hand and they would say, I want to be stable. I want to be stable. Because almost all of them are not stable, except for, look at your periodic table now, that last group, group 18, the last group, they're all stable. All right, those are called the noble gases, that group 18. And they start with helium, they go to neon, then they go down to argon, krypton, xenon, and radon. Group 18s are already stable, okay? They're like a person, and these are probably rare, it's like a person who doesn't need a relationship anywhere. They're just perfectly content by themselves all the time. All right, I'm thinking hermits up on the side of a mountain. They don't need a relationship. They just like being with themselves, and that's it. Okay, they're already stable just by themselves. So they don't form bonds with things. They don't form because they're stable already. But the rest of them, their hands are up. They're like, we want to be stable. We want to be stable. We want to bond with something where we're stable. We don't have a charge. All right, so it's kind of like you. Maybe, I hope this analogy applies to you. I'm trying to use a lot of analogies in this. An analogy is a comparison of something you don't understand to something you do understand. So I'm trying to like compare chemistry to analogies. Hopefully it works for you. But elements may be like you. In other words, you want to find that one right person for you. You want to find a relationship where you're completely content and happy with that relationship. And you don't want that relationship and then extra relationship, do you guys? No, no. You want that relationship, and that person just meets all of your needs, and you're so happy with that person that you don't need other relationships other than that. All right? In other words, you want to be stable. You want something else. You want to be stable. You don't want to be stable plus 1, plus 2. You want to be bonded with somebody where you're stable. Okay? You also don't want to be alone. In many ways, chemically speaking, that's like being a negative number, a negative charge of some sort. Okay? You can be alone, having a negative charge, and kind of go, I wish I could bond with somebody. I wish I had somebody. It's just me. I want a stable relationship. That's kind of like the elements. The elements are all saying, we want to be stable, we want to be stable. We just want to have a zero charge, But electrons, protons, and neutrons will dictate how much charge that an element has. For example, let's say we're talking about this element, and all of you should tell me what this one is. You should be able to look at it and say what it is without looking at that periodic table. This is lithium. Okay, lithium, if you check it out now on the periodic table, it is number 3. It's number 3 in the periodic table. And it's in the far left-hand column, which we call in chemistry group 1. They're the group 1s. All right, lithium in group 1 has what we call an oxidation number. Now don't freak out about oxidation numbers. That's what we call a charge. It's a charge that the atom normally takes. In other words, lithium has an oxidation number of +1. In other words, it has 1 electron it wants to give up to be stable. It wants to give it up to be stable. It's number 3, but it has a +1 charge, which means it has an extra electron. In other words, for lithium to be stable, we're going to look at valence shell diagrams here for a second. Let's just look at electrons for a second. It has a total of atomic number 3, and it has 3 total electrons. Now on the first shell, and atoms are going to have shells that build them bigger and bigger, kind of like those gobstoppers, I think they're called. Those big old things of candy you put in your mouth and you dissolve away layers and they turn different colors as you get them smaller and smaller and smaller. Well, atoms have those layers, we call them valence shells. They're valence shells. And the very first layer closest to the atom can only hold 2 electrons. For all of them, they can only hold 2 for the first one. It doesn't matter if it's chlorine, doesn't matter if it's sulfur, it doesn't matter if it's lithium, they hold 2 in the first shell. And now the next shell out, remember lithium is number 3, it has 3 total electrons, excuse me. The only amount that it can have in that shell is 1. Okay, so it has 1 in the outer shell, 1 negative charge out there. Now lithium is looking for something to give that electron to form a bond with. It's looking to give it up. Lithium is kind of like you if you have a game of chess. I don't know if you've ever played chess, but you have a bunch of pieces. And let's say you really want to play a game of chess, but you're plus 1 piece. So you have an extra pawn. You have all the pieces you need, but then you have an extra pawn. So if somebody comes around and they say, oh my gosh, I want to play chess, but I don't have all the pieces, I need a pawn, you're likely going to go, hey, wait a minute, I got an extra pawn here, I'm fine if you have this extra pawn. In fact, I'll be happy to give it to you. In other words, they're likely to bond something that needs 1 more. And that's going to come into play later. All right, so lithium's valence shell diagram has 2 electrons in the first shell. It has 1 electron in this shell. And this electron is saying, I want to be stable. Remember, lithium wants to be stable. So it says, I just want to be stable. It's not stable with 3. It's only stable with 2. And so it's saying, I want to give this one up. But then you have another element, chlorine. I want you to go to your periodic table now. I want you to go find it. I believe it's, I just lost, oh my gosh. It's in group 17, I know that, and chlorine, is it number 17? Yeah, it's 17. It's also in group 17. In other words, it's right next to the noble gases. Look on the far right side of your periodic table. You got the noble gases, group 18, and then you have what we call the halogens. The halogens, chlorine's in the halogen group. You got to know the halogens, guys. Halogens are fluorine, chlorine, bromine, iodine. Those are all halogens. Okay, I call the halogens hell raisers. They're hell raisers because they will rip any electron off anything that wants to give up 1 vigorously. All right, they're kind of bullies. They go around, they bully their way around. In fact, they're very dangerous. That whole halogen group, if they're isolated by themselves as elements, I've erased it already. They're dangerous. Chlorine by itself is very, very dangerous. And it's only stable when you bond it to something else, like sodium, to make sodium chloride, which is table salt. Table salt's safe, but chlorine by itself, because it also says, I want to be stable, except chlorine says, I want to be stable, and if I'm not stable, I'm going to wreak hell everywhere around here, and I'm going to cause all kinds of damage. Chlorine is deadly by itself, by the way, and so are the other halogens. They're very dangerous. Now, chlorine comes around, and chlorine is 17. All right, it has 17 electrons. So the first shell, it fills it up with 2. But then the next shell, which in chemistry holds 8, total 8, and the next shell also holds 8, it's going to fill those up with 8 more. Remember, it has 17. So far, we have a total of 10. Okay, but it also has another shell. Chlorine goes out, if we're doing a valence shell diagram for chlorine, and it has 8 plus 2 makes 10, its total is 17. So how many go in that last outer shell? And the answer for that is 7. Now, it wants to be stable at 8. 8 makes it stable. It has 7. It's kind of like you if you sit down and play a game of chess, and you count up all your pieces, and you're missing 1 piece, but you really want to play chess. You're probably going to go, oh my gosh, I can't even play. I just need 1 piece. Can anybody give me 1 piece? Except if you're chlorine, you don't go, can anybody give me 1 piece? You go around and you say, oh, I see you got a piece. I'm going to come take that piece from you. And it will actively pull electrons close to it. And like a bully, picking on people that have extra, it'll go up and it'll pull that electron, especially from elements like lithium, and it'll form a bond, because if it takes this electron away from lithium, then it can fill up its outer shell. Chlorine will be happy because it'll kind of move to 8. And then lithium, guess what? It also is happy because it's stable at 2. First shell holds 2, next hole's 8, next hole's 8. We're going to get to all this. This is how it works. So chlorine essentially is a -1 because it's saying I want to gain 1 electron to become stable. Lithium saying I want to give up 1 electron to become stable. So they make a good pair for this. Okay, so hopefully this is making sense. This is basic concepts in chemistry. They're all saying that we want to be we want to be stable. All right, so we're going to the next little concept. The next concept is not far from this. This is called electron dot diagrams. We're going to look at electron dot diagrams, and we're going to see how a valence shell diagram, which is like this, is different than electron dot diagrams. Many times they're called dot diagrams. Now, if you do a valence shell, like we showed just now, you're showing all the electrons in the different shells, okay? All the layers of gobstopper colors from the outside, from the inside to the outside. But now we're going dot diagrams, and in dot diagrams, all you do is show outer electrons, just the outer electrons. You're not showing the other ones. So you just need to worry about that last shell. And let's go back to lithium. Remember, lithium is in group 1, and they all have 1 electron they want to give up. Group 2s, they all have 2 electrons they want to give up. Can you go to your periodic table right now and find an element that has 2 electrons that's ready to give up? Go ahead, go find one. In fact, find the lightest element, the earliest in the periodic table that has 2 electrons to give up. And if you know what you're doing, then you have found number 4, beryllium, Be. It also has 2 it's willing to give up. So its oxidation number is +2. It has +2. The one right below Be, which is Mg, magnesium, it's also a +2 oxidation number. It wants to give up 2. But if we're going to lithium and we're doing a dot diagram, you don't show the shells, you just show outer electrons. And so let me show you how easy this is. Lithium's dot diagram is written like this. You just have 1 electron in the outside. That's supposed to represent an electron, a negative charge that spins around the atoms. And so it's like this. It's basically saying I've got 1 electron, anybody want it, and things that want it will bond to it. But if you go to, say, magnesium, symbol for magnesium is this. It's a +2 because it's in group 2. You go for magnesium, you put 2 dots on the outside. You gotta have 2 for that one. Okay, magnesium is willing to give up 2 pieces, and it will bond with things that are likely to bond with 2 extra electrons given up. Now let's do one a little bit weird. Let's go to oxygen, and we're gonna do oxygen's oxygen's dot diagram. Write the symbol for the element, and then you find out how many total electrons does it have. And oxygen's total electrons is going to be 8. It's going to be 8 total electrons because it's atomic number 8. Alright, so if we're doing a valence shell for oxygen, which is sometimes the easiest way to do that, you know the first shell is filled up with 2, the second shell is filled up with 8, but it doesn't have 8 more, because it has a total of 8. So 2 plus something is gonna represent however much is gonna fill this up. In other words, it's gonna be 6. 6 plus 2 represents the total number of electrons that oxygen has. That's 8, because it is atomic number 8, and so it has 6 in the outer shell, which means it likes to pick up 2, and it's like a 2 negative oxidation number, 2 minus oxidation number. It's trying to pick up 2 negative charges to be full on the outside and be a stable bond. So if you're doing a dot diagram for this, you're not showing 2 at all. You're showing 6 total electrons in the outer shell. I like to write them 2. There's 2 electrons. There's 2 more electrons. There's 4 total electrons, and there is 6 electrons, which is the dot diagram for oxygen. Okay, if they're stable, you would actually put 2 more right here, and those would only be the noble gases that are stable, and the noble gases would have a full 8 on the outer shell, and they're all happy, they're all good the way they are. Alright, so I'm hoping that you're getting the basics on these compounds. I'm hoping it's making sense for you. So if you like this video and it makes sense to you, then click the thumbs up button and like it. And if you want to see the next video, then click over here on this square on this next video, and it will automatically take you to the next video. Actually, I just lied to you. I don't really know how to do that, to make the square come up and then you click the next. No, I'm not that good. I just always wanted to say that, guys. I always wanted to say it. So just look into my series. You'll find the next video, and the next video should be PS3 in the next video. Right now, this is Mr. B, and I'm signing out from my workshop. You guys have a good day.